just get started with our opener. First, thanks so much to our sponsors, Information Insights, GVEA, Golden Valley Electric Association, and our Southeast Conference, as well as Alaska AHFC, Alaska Home Finance Corporation. These are our sponsors that make today's presentation free, unless you're taking this class as a CEU, and then we have a link for $20, which just helps us with those processing fees for the CEU through the state. So if you're here in not wanting to get or earn a CEU, thanks to our sponsors, that is a no cost. Today on the line, we have Laura Grange. She's with Information Insights, and she is hosting the Zoom call today. So you'll see information from her in the chat. And Dr. Tom Marsik is our speaker today on heat pumps for homeowners, or for realtors. And heat pumps for homeowners is actually our next class and our final class of our spring session. It will be held next week, May 23rd, from 5:30 to 7 p.m. And in the chat, Laura just posted a poll and a quiz that should have just popped up onto your screen. If you wouldn't mind just taking that for us, it gives us some great information about who is in the room and how we can improve these classes in the future. And we will also provide another poll at the end of the session as an exit poll. So at this time, I will introduce Dr. Tom Marsik. He's the chief scientist at NREL's Alaska campus in Fairbanks, Alaska. He has a joint position with the University of Alaska Fairbanks and the Cold Climate Housing Research Center, where he serves as an associate professor of sustainable energy for the UAF Bristol Bay campus and Alaska Center for Energy and Power, or ACEP. He wears a lot of hats. His work in the areas of energy and sustainability utilizes the synergies of this joint position to benefit the people in Alaska and beyond. Tom has been awarded Alaska's Top 40 Under 40 and has been recognized for the World Record Academy for designing and constructing the world's most airtight residential building on record. Marsik has numerous publications that has served on high-profile communities, including Alaska Governor Bill Walker's transition team and its Consumer Energy Subcommittee. His daughter is a daily reminder to work hard on achieving sustainable future. And I love that. And so pleased to have Dr. Marsik here today. So Tom, I will hand it over to you.
Well, thank you so much for the introduction, Mindy, and thank you to you and Laura for organizing these exciting events. And of course, thank you to all participants for the opportunity to chat with you about heat pumps for realtors. So let me share my screen here with the presentation. And I should clarify right at the beginning that my background is not in real estate. My background is in heat pumps only, as far as this class goes. So I'll be able to explain what a heat pump is. So that way, when you guys see this thing in a home, you have a basic idea of what it does. But I'll be relying on you and your questions to lead us to the information about heat pumps that is important from the perspective of real estate. So please keep those questions coming as we go through this class. So just a brief outline of the things that I am hoping to cover. So I'll go through a basic introduction, basic concepts of heat pumps. Then I want to look at comparing different types of heat pumps. Then we'll focus on air source heat pumps specifically. Afterwards, I'll tell you what we know so far about how they perform in our cold climate in Alaska. I'm going to show you some resources about heat pumps. Then I just want to quickly demonstrate what kind of savings can be achieved if we combine the heat pumps with other energy efficiency improvements. We'll talk briefly about financing and incentives available for heat pumps. I'll try to then draw some main conclusions. And at the very end, I would like to do a live demonstration of an online heat pump calculator, which is a very useful tool that allows you to evaluate whether a heat pump makes sense in a given building or not. So that's a brief outline. Again, the topics I am hoping to cover, but feel free to jump in with questions and other things that you are interested in. Okay, so what is a heat pump? So a heat pump is a device that takes heat from a cold place and puts it into a warm place. So that's the opposite of what's happening naturally. So naturally, heat flows from hot to cold, but we can reverse it by using a heat pump. So we can make it go from cold to hot. And you all are probably familiar with heat pumps because you all are probably used to using a refrigerator. And a refrigerator is a heat pump. So your normal household refrigerator takes heat from the cold place, that's the inside of the fridge, and puts it to the outside. That's why the coil on the back of the refrigerator is hot, because that's where the heat is going. And the same thing with a freezer. Just think of a freezer where you might have, say, 0 degrees Fahrenheit inside the freezer, and it's working. It's taking the heat from the inside of the freezer, from that very cold environment, and putting it to the outside of that freezer. So again, the coil on the back of the freezer is hot. So that's what a heat pump does, and we can use that for heating buildings. So we can have it installed in a building, so it's supplying the heat to the inside of the building, but now it's not removing the heat from the inside of a freezer, it's removing the heat from the outside environment. And that outside environment, it can be the air, then we are talking about an air source heat pump. It can be a body of water, then it's called a water source heat pump, or it can be the ground, then it's a ground source heat pump. The heat pump that you will most likely see in buildings is the air source heat pump. So we are going to focus on the air source heat pumps in this class mostly. There are situations where you could see the other types of heat pumps, but they are going to be more rare. So most likely you'll see the air source heat pump. Here's a picture of an air source heat pump. So this is the device that's sitting outside, and that's the one that's extracting the heat from the outside environment, from the outside air. And then this is the unit that's inside. This is the one that you will probably see the most likely, even though there are other types, but these wall mount units are the most commonly used. So it's typically up high, close to a ceiling, and it's blowing warm air here into the indoor space. How does a heat pump work? It's not magic. It's physics. If anybody's interested, in the details of that, I can go briefly over that. It has a compressor, and it has a working fluid that we call the refrigerant. And at this stage, when it goes to the compressor, it's in the form of gas. And the compressor compresses that, and you know what happens when you compress gas? It becomes hot. And so then it sends this hot gas to the indoor unit, and this hot gas in that indoor unit is then transferring the heat to the indoor environment in the building. So that's how it's heating the building. And with that refrigerant is being cooled down as it's transferring the heat to the indoors of the building. And as it's cooling down, it condenses into a liquid. And then we send the liquid out to the outdoor unit, and we let the liquid evaporate in the outdoor unit. And then through the evaporative cooling, it actually cools itself down below the temperature of the outside air. And then the heat from the outside air then is transferred into this refrigerant. And then it goes into the compressor again, where it's compressed, heats up, and the cycle continues. So again, it's not magic. It's a refrigeration cycle. But it's important to know that it needs the compressor for this to operate. That's at least the most common system that's being used for heat pumps. The one that's using compressors, which means we need electricity. So the heat pump, even though it might be saving you fuel in a building that you might otherwise use for heating, now we have this heat pump that needs electricity. And we'll look at some of the trade-offs between that. So what are the advantages of heat pumps? They are relatively low maintenance. They have no combustion on site, at least. They are partially renewable because the heat is in the outdoor environment thanks to things like the sun. They can be fully renewable if the electricity for the heat pump also comes from renewable sources. And they have the potential to lower energy use and energy costs. And it's because their efficiencies are greater than 100%. And that's why we don't really call it the efficiency, we call it the coefficient of performance. Now, how is that possible that the efficiency is greater than 100%? Again, it has to do with physics. We know from the laws of physics that energy cannot appear or disappear. So the energy you put into the heat pump in the form of electricity ends up in the building in the form of heat. And then in addition to it, the energy that you extract from the outside environment also ends up inside in the building. So the amount of energy you get in the building in the form of heat is greater than the amount of energy that you put into the heat pump in the form of electricity. Now, how many times greater it is, that's what the coefficient of performance tells us. So this is an important parameter that describes how efficient that heat pump is. If the coefficient of performance is, say, 3, then it means for every unit of energy you put into the heat pump in the form of electrical energy, you get 3 units of energy in the form of heat into the building. It's because that 1 unit you put into it ends up in the building, and then the 2 additional units are extracted from the outside environment and they end up in the building also. So this is an important parameter that you are looking at when you are evaluating or comparing heat pumps. The Alaska Center for Energy and Power did a great job evaluating what's currently in Alaska as far as heat pumps installed, and they compare them from various perspectives, but one of them was the installed cost. So here is on this chart on the y-axis, that's the installed cost per 1 unit of thermal output, and on the x-axis, there's the size of the system. It makes sense to compare them on the basis of the cost per 1 unit of thermal output, because obviously bigger systems are going to be more expensive. But what we know to know how they compare on the basis of the cost per 1 unit of thermal output. And when you look at the graph here and look at the dots, they are kind of all over the place. We cannot make any solid conclusion. At least seems like that. To say that one type is cheaper than the other type. And it's because, and this is the install cost as shown here, and it's because there are many factors that affect the cost besides just the type of the unit. It's also how are you going to bring the source to the heat pump, how are you going to distribute the heat then throughout the building. So there are lots of aspects that do go at the end into the install cost. But one observation we can make from this, and that relates to this, what looks like a gray dot here in the lower left corner, but I'm telling you it's actually 4 dots on top of each other. And all these 4 dots refer to ductless mini-split systems. So ductless mini-split system, that's what I showed you in the picture before. So it's an air source heat pump. So it's pulling out the heat from the outside air, which means there is no cost to bring the source to the heat pump. And they are ductless, which means there is no cost for the distribution system inside in the building. And that's why you can see that here it's the lowest install cost per 1 unit of thermal output. And because of that, these are the ones that are getting currently a lot of attention in Alaska. So it's these ductless mini split systems. Again, that's what you saw before on the picture. And because there's a lot of attention going to the system, a lot of interest, and that's what we are focusing a lot in our research, and that's also what I'm going to be focusing a lot in this class. Because when you go to a building that has a heat pump, likely it is going to be this ductless mini split heat pump. So the Alaska Center for Energy and Power also compared these heat pumps from the perspective of the efficiency, which we know is described using that coefficient of performance. And here it's shown as a function of the average input heat temperature. So that would be temperature of the source. If it's an air source heat pump, then this would mean the outside temperature, which is where we are taking the heat from the outside air. And when you look at the data points here, they are again all over the place. It seems like we cannot make any conclusion about the efficiency based on the type of heat pump. But there are a few observations we can make here. And one of them is that when you look at the heat pump with the highest efficiency here, so that's the COP, the coefficient of performance of about 4.5, that's a ductless municipal heat pump in Wrangell, Alaska. But the fact that the highest efficiency here is one for a ductless municipal heat pump doesn't mean that we can just say, okay, so the ductless municipal heat pumps are the most efficient, because when you look at the dot that has the lowest efficiency here, so that's the lowest COP of about 1.6, it's also a ductless municipal heat pump. This one was in a building in Dillingham, Alaska. As you can see, this was also in a much colder environment compared to the one in Wrangell. So while we cannot make any strong conclusion about a type of heat pump that would be the most efficient, one conclusion we can make from this is that if we use the ductless municipal heat pump in an appropriate situation, and we use it in the correct way, we can achieve a very high efficiency. So which means we can be saving a lot of energy and a lot of money on the energy bills. So that's the conclusion we can make, that if we use it right, then there is a huge potential for savings. So how do we use it right? I'll get to it later in this presentation. So there is, of course, a fundamental challenge when we are using air source heat pumps, and it is that the colder it gets outside, the higher is the heat demand for the building, obviously. But the heat pump does the opposite. The colder it is outside, the more difficult it is to extract the heat from the outside air. Excuse me. And so you end up with a heat deficit, and at some temperatures, the heat pump might stop working altogether. So, at the point when you need your heat source the most, it stops working on you. So that's obviously a fundamental challenge with respect to air source heat pumps. So that's an important consideration, that you need a backup heat source in cold climates, like Fairbanks, for example. When it's 40 below in winter in Fairbanks, there is no heat pump on the US market that could be effectively delivering heat at 40 below. So you do need a backup heat source together with the installation of your heat pump. Then another consideration is, so what is the source of electricity and its efficiency? If it's a heat pump installation in Southeast Alaska, where the electricity is coming from a hydroelectric power plant, it can make a really good sense to use a heat pump. Now, if you are, say, in rural Alaska, where people use diesel for heating homes, heating oil for heating homes, and those communities also often use diesel for generating electricity, then really we need to ask ourselves the question, well, does it make sense to be burning diesel in the power plant to produce the electricity for the heat pump, when we can just take that diesel and burn it on site in an all-fired heating system for that building? And when you look at the numbers, kind of an efficient diesel generator is, say, 35% efficient. An efficient oil-fired heating system is, say, 85% efficient. 85% divided by 35% is about 2.5. So we need the coefficient of performance to be at least 2.5 for the heat pump to be making sense in that situation. Otherwise, the amount of diesel you burn in a power plant would be greater than if you just simply heat with heating oil in an all-fired heating system for that building. So that's kind of, the magic number for rural communities is typically the COP about 2.5, but this really varies by community depending on where the electricity is coming from. In Fairbanks, for example, the threshold is roughly at the COP of 2. So again, it's because of the mix that we are using in Fairbanks for electricity generation. So another consideration, are you going to be using air-to-air or air-to-water heat pumps? So what I showed on the picture before, the same picture is here. So it's an air-to-air heat pump. It's taking the heat from the outside air and supplying it into the inside air. Another type of an air source heat pump would be air-to-water, where you have hydronic distribution then throughout your house, just like you would have with your oil-fired boiler, for example. Most likely in a building, you will see the air-to-air heat pump. Again, because the popularity of the ductless mini-split systems. Some buildings do use the air-to-water heat pumps, but those are relatively rare compared to the air-to-air heat pumps. Now for the air-to-air, are you gonna use ducted or ductless systems? So what you see here on the picture is a ductless system. So there are no ducts that would be distributing the heat. It just has, this indoor unit that's just directly blowing warm air into the indoor environment. And again, these are the most popular in Alaska. With a ducted system, it's a possibility also when you have a central unit. And then with ducts, you are distributing the warm air into the indoor rooms. But there is typically a much higher capital cost associated with that. And that's why, again, most interest is here in these ductless mini-split systems. So that's what I'm going to be mostly focusing on in this class. Now, when you are using the ductless mini-split heat pump, there's, when people are installing it, they need to make the decision, are they going to use an external thermostat or a built-in thermostat? So an external thermostat would mean that, somewhere on the wall, there will be the thermostat that's sensing the temperature in the room. But that's an additional cost when installing the heat pump. So again, those are fairly rare. When you go to a building that has a ductless mini-split heat pump, most likely it's going to be one with just a built-in thermostat here on the inlet of the unit. Then another consideration, of course, is what is the outside air cutoff temperature if you want to be able to use the heat pump in very cold environments in Alaska. So how do they perform in Alaska? So we did a couple of studies. So I'm going to tell you first about one we did back in 2014, 2015, where we evaluated the field performance of some installations in Alaska. And so here on this map, you have the locations of those installations. And the green ones is when we did kind of a general evaluation, and the orange ones, there was in Dillingham, Juneau, and Wrangell. That's where we evaluated the performance in a much greater detail, which a lot more sophisticated instrumentation of those heat pumps. And I'm gonna show the results from the detailed monitoring. So those 3 heat pumps that we evaluated in a greater detail. So here are the results on the x-axis. That's the outdoor temperature, and on the y-axis, that's the coefficient of performance. And I should point out that we looked at both. We looked at the steady state coefficient performance and also the integrated coefficient of performance. And one can kind of see pretty well what the differences between those two. In this series, the one with the blue dots and the black dots, so this was an air-to-water heat pump in Juneau. And when you look at the data from that, you see that in the temperature range, somewhere from around 40 degrees Fahrenheit to say 45 degrees Fahrenheit, the black series is pretty much lined up with the blue series. And it's because in those temperatures, the heat pump does operate in a steady state. So that's why we are seeing the same level of the coefficient of performance. But what happens in the warmer temperatures is that now, you know, it's warm. Your building doesn't call for too much heat, and the heat demand of the building is actually below the heat rate that the heat pump is supplying, even at the lowest compressor speed. And so the only way that the heat pump can satisfy it is through cycling. So it's simply turning on, turning off, turning on, turning off. And that's decreasing the efficiency of the heat pump. So that's why these black dots here. So that's the true efficiency. So this is the integrated coefficient of performance is lower than the steady state coefficient of performance. So the blue dots is, you know, when it's just running steadily, what the efficiency would be. But the black dots, it takes everything into account to show the real efficiency. So that's the integrated coefficient of performance. Now, what happens in the colder temperatures here? So below, you know, say 40 degrees Fahrenheit or so. So remember, the coil of the outside unit needs to be colder than the outside air in order to be able to extract the heat from the outside air. And so in those temperatures, the coil of the outside unit is below freezing. And when it's below freezing, there's condensation on that coil, and the condensation is turning into ice because it is below freezing. So the outside coil is frosting up. It's slowly building up ice on that. And the unit needs to defrost itself every so often. So it goes through defrosts. And so because it needs to cycle like this, you know, it runs, but then it goes into a defrost. And what it does in the defrost actually reverses the mode of the heat pump, you know, as opposed to using it for heating. It takes a little bit of heat from the inside of the building and it sends it to the outside unit to get it really warm, you know, above the freezing point, to melt the ice on that unit. So it's reversing itself for a little bit, and then when it melts the ice, it goes back into the normal operation. But because of these cycles, you can see that the efficiency is reduced, and that's why the black series, so that's again the true efficiency, the integrated coefficient of performance, is lower than the blue series, which is the steady state coefficient of performance. Now, one thing that we found out through the study, and this relates here to this series with the green and red dots. So this was a ductless mini split system in Wrangell, Alaska. We found out that with a lower thermal loading of that heat pump, we had higher efficiencies. And what I mean by the lower thermal loading is that this heat pump was a little oversized. So it wasn't running any close to its maximum capacity. It was running at a much lower capacity. And what we found that with the lower heat output, the efficiency was actually increasing. The coefficient of performance was higher than what it would be otherwise if it was running at its full capacity. But then with this heat pump, that's this series, that's the blue dots and the purple dots. This was a ductless mini split heat pump in Dillingham, Alaska. We found actually the opposite. We found that with the lower thermal loading, the coefficient of performance was decreasing. Now, this wasn't the purpose of the study. This is just something that we noticed, and it created a research question that we plan to then address later, and we did. I'll talk about it in just a little bit. But I'm pointing it out here to show that there are still some unknowns with respect to the operation of heat pumps in Alaska. And with the research we are doing, there is a potential for improvement in their efficiencies. And so we can expect the heat pumps being more and more popular as the research goes on and on. For one, with the improvements in the heat pump models themselves, and for two, with our improved understanding of how to use them in Alaska. So again, I'm saying this just to point out that likely we are going to be seeing increase in the use of heat pumps in Alaska. So one thing that I should point out on this graph too. So we talked about the magic number for the COP. When in rural Alaska, typically like COP of 2.5. In Fairbanks, like a COP of 2. So as you can see here, if you want to have a COP of 2, that's the coefficient of performance, or greater, which is when it's beneficial. If you are below the COP of 2 in Fairbanks, it just means that the electricity that you are using for the heat pump is too much compared to the heating oil that the heat pump is saving you. And as you can see, it's very challenging in the very cold temperatures to achieve a COP that would be greater than 2. So this is important to understand, where the heat pumps are beneficial to use, like this area here, in Wrangell, Alaska, with you're looking again at COPs, 4 or 5 or even a little higher in much warmer temperatures. That's where the heat pump can be very beneficial. Plus the electricity there is coming often from hydroelectric power plants. Unlike say in Dillingham, in very cold temperatures, for one, the heat pump is now using a lot of electricity because the COP is low, and for two, the electricity is coming from diesel. So these are the things we need to be factoring in to decide if the heat pump is appropriate for the given building. And of course, a common way of operating the heat pump is that you would only operate it at the warmer temperatures and not operate it in the colder temperatures when it doesn't make sense to operate it. So you would simply be turning off that heat pump in those colder temperatures when it would just be wasting energy. So some of the general conclusions from this detailed monitoring. So we found that the transient operation, which means when it's not in a steady state, and this is due to the on-off cycling, which in a cold climate is because of the frequent defrosts, can significantly reduce the performance. So this is one of the important research fields, is how to optimize the defrost controls for cold climate operation to increase the performance. So again, this is I know you are probably not interested in all the detail about the research, but this is the message of this is there is research going on that's aiming to increase the performance of heat pumps in Alaska, make them more viable, and we are likely going to see higher use of heat pumps in Alaska. Also, there are large variations in efficiency among individual models. So we do want to pay attention when we are selecting a heat pump for a given building. When I talk about the cycling due to defrost, here is a graph that just demonstrates what I mean by that. So the green series here, that's the thermal output, and as you can see, the heat pump is running. Then the output start kind of dropping here. It's because now the coil is really icing up outside on the outside unit. And now it's so iced up that the heat pump decides to go into a defrost, and it shuts down the output. It reverses, it has a reversing valve, so it reverses it from heating to cooling for a little bit. It's cooling the building and supplying the heat to the outdoor unit to defrost it. That's why the blue series here, that's the electricity going to the heat pump. It's still using electricity even though it's not supplying any heat. And once it's defrosted, it switches back to the normal mode. And again, you can see, the green series, it is supplying heat into the building. While talking about this, I should point out that that's another advantage of heat pumps, is that at the same time they can provide cooling for the building. During hot periods of the year in the summertime, if you do have a heat pump installed, then just with a switch of a button you can reverse it, and then in the summertime use it for cooling. There are some additional installation considerations, because when you're using it for cooling, it can create condensation of the moisture in the indoor air, and you need to route it somewhere from the heat pump. So that's a consideration to keep in mind. But as long as it's installed, then again, it's just a push of a button to switch it from heating to cooling. Also, I talked about the short cycling in low load conditions, when it's warm outside and the building doesn't need much heat. So then the way the heat pump is going to be satisfying it is simply through turning on and off. So here you can see those cycles as an example. Here, like the green series, there's the thermal output of the heat pump, and as you can see, it's like 5 minutes on, 5 minutes off, 5 minutes on, 5 minutes off. And again, this cycling reduces the efficiency of the heat pumps. So sizing properly the heat pumps is an important consideration. And we do have more research to do in that area about how to size the heat pumps. So I mentioned that we monitored more heat pumps. Just the detailed one was for 3 heat pumps, but we had 30 heat pumps where we did general monitoring, and it was a mix of ductless heat pumps, then the ducted heat pumps, and there are some air-to-water systems in it also, and a mix of commercial and residential systems. Some were retrofit appliances, which means there was an existing building with an existing heating system, and the heat pump was added to it. So there was a retrofit where the heat pump was added to it, and some were new installations, which were new buildings that were only built with the heat pump in mind. And so the findings from this were that 29 out of the 30 systems provided adequate or expected heat. There were 2 repairs needed, but both were fixed at no cost to the building owner. 11 people perform maintenance on the system, but it's typically very simple maintenance. It's basically all that the heat pump needs is cleaning the filters on the indoor unit once in a while, which is a simple process. And 12 people used their backup heating system, although 29 people had backup heat available. So overall, people are happy with their heat pumps. So if you are interested of what is the current research doing, here is a project that we recently concluded. It was a lab study, and this was this research question again was initiated by what we happened to notice before in the field, how the coefficient of performance was changing with different levels of thermal loading. So here we studied 4 different heat pumps in a cold chamber in a lab, and at each temperature in the cold chamber we were able to simulate the outdoor temperature, and at each temperature we were measuring the performance of the heat pump with the different level of thermal loading, and then at the end we were curious, so how does the coefficient of performance vary different with the different levels of thermal loading, and so we were able to find out that this is what the relationship is, that if you have a heat pump that's running at its full capacity, and now you can unload it a little bit, it's gonna increase its coefficient of performance. But if you continue reducing that thermal load, then the coefficient of performance starts dropping. So there's kind of a sweet spot for that heat pump. And again, this is kind of a step towards being able to provide better guidelines for how to be sizing the heat pumps. So if you have an oversized system, it's not gonna run at its full capacity. If you have a big heat pump for a small building that's efficient, it's not gonna run at its full capacity. So it's gonna run at a partial loading. But then if you overdo it, then it's gonna run at that level of thermal loading that's too small and significantly reducing the coefficient of performance. So correctly sizing the heat pumps is tricky, and we have more research to do in that area. And then when you look at the efficiency of the heat pump, here is on the x-axis is the outdoor temperature, on the y-axis is the coefficient of performance, and now the blue series is the coefficient of performance at the maximum level of thermal loading. So the heat pump is running at its full capacity, and now the orange series, it's when it's running close to its peak here. So here the blue dots correspond to this this point here when it's at the maximum thermal loading. The orange dots are these points here that are close to its peak. So we do see that we have a potential to increase the efficiency of heat pumps with proper controls and proper installations. But it's a research field. It's not easy because the relationship is not simple. So again, for those of you not really too interested in the details of the research, the main message of this is that there is quite a bit of research going on to improve the efficiency of heat pumps in Alaska, and likely we are going to see more and more heat pumps installed in Alaska as they are getting better in saving energy. So here are some of the heat pump resources for you and for homeowners or potential buyers of buildings with heat pumps. So the Alaska Heat Smart is an excellent resource. They are located in Juneau, so some of the resources are Juneau specific, but they also have a lot of resources that are applicable to anywhere in Alaska. Then, of course, the Cold Climate Housing Research Center. Then there is the Alaska Mini-Split Heat Pump Calculator, which I'm going to demonstrate how to use here in just a little bit. That will help you determine whether a heat pump is suitable for a given building. Then there are some national resources like this Northeast Energy Efficiency Partnership, also international resources. This one is from Canada. There are more detailed classes on heat pumps, for example, by Carter and Nosan or Wisdom and Associates. Then there's a database of incentives for renewables and efficiency, also a very useful resource. So when we talk about heat pumps, we shouldn't forget about other things we can do to buildings to save energy, because obviously the biggest savings can be achieved with a system approach when we combine the heat pump with other energy efficiency measures. So this is just an example of an extremely energy efficient building in Dillingham, Alaska. So it's extremely insulated. This building has 28 inches thick walls actually. So it's that's what I mean by extremely insulated. It's extremely airtight. It's using an air source heat pump. You can see it installed here. Here's a more detailed picture of that, and then the indoor unit, and this this home in Dillingham, Alaska. It's just using the heating cost is like a few $100s annually, which is a small fraction of what most homes in Dillingham pay for heating. So this is just to demonstrate what kind of savings can be achieved if we combine a heat pump with other energy efficiency measures. So how do you decide if heat pump is the best thing to invest into, or are there other things you should be investing into first to make the building more efficient? So again, if a potential home buyer is looking at a building that maybe is not so efficient and wondering, maybe they like the building from other aspects, but wondering, well, what can they do to make it more efficient? Well, the best first step is to get an energy audit. So get an energy auditor, and the energy auditor is going to come into the building, and the energy auditor is going to do a blower door test. It's a test to find out how airtight that building is, and they will probably measure the walls and investigate what kind of insulation there is. Look in the attic if there's an attic, look in the crawl space if there's a crawl space, and then they are going to process the data, and they'll give you a report that, among other things, is going to have a list of the improvements you can make to the building, and that list is typically prioritized. So the first things on the list are the things with the shortest payback. And so this is the first best step is to get an energy audit, and an energy audit will help you determine what are the things that make the most sense to start with. And then from that you will be decide, well, is this the right point to install a heat pump, or should you be investing into other things first? So there is financing and incentives for heat pumps, and a lot more is coming actually, through the bipartisan infrastructure law and through the Inflation Reduction Act. So it's being processed now, and a lot more financing and incentives are coming. for heat pumps and energy efficiency and renewable energy. A good resource for the current financing incentives is, again, the Alaska Heat Smarts website. So when you go to the Alaska Heat Smarts website, before then I showed the resources. So this was one of the link, akheatsmart.org. And when you go to financing incentives page, it's a great resource for what is currently available. And I realize, so you as realtors, you might also run into a situation where maybe there's a building that's being sold that might have a failing heating system. And then that system will need to be upgraded by the new owner, and that might be the good point in time to evaluate if a heat pump makes sense. If you need to upgrade the heating system anyway, are you just gonna, if it's an all-fired boiler, for example, in Southeast Alaska, are you just gonna replace it with a new all-fired boiler, or maybe would it make more sense to replace it with a heat pump instead? So that's just another situation where a heat pump could make a very good sense to look into. So here are some main conclusions from what I have covered here so far. So we see that the air source heat pumps can significantly reduce energy use and energy costs when used in appropriate situations and done right. So it's important to keep in mind, it doesn't mean we should be installing heat pumps everywhere, because there are situations where they don't make a good sense. So we want to be knowledgeable about where they make sense. So we install them all in those situations when they do make sense. And we have more research to do. So more research is needed to gain a better understanding of the performance of current air source heat pumps, so we can inform the decisions regarding future installations and operations in cold climates. So one of the things we are still figuring out is how to properly size the heat pumps in Alaska, how to properly control them to maximize the efficiency. And again, with that, we are expecting that the heat pumps will be getting more and more efficient, and will make more and more sense even in locations when maybe historically they did not make sense, but because of the increased efficiencies, now they are going to be starting to make sense even in those locations. And of course, system approach yields biggest savings. So as you can see, if you combine a heat pump with other energy efficiency measures, that's when you can yield the biggest savings. Lots of people and entities help with these projects, so big thank yous. We couldn't have done it without them. And like I said, now towards the end, I would like to do a live demonstration of this very useful tool. So that's the Alaska mini split heat pump calculator. It was developed by Alan Mitchell of Analysis North. And like I said, we still have some gaps in understanding how the heat pump behaves in cold climates. But Alan just did an amazing job of compiling what we do know about heat pumps and using it to create this tool that comes up with the best estimate of the performance of the heat pumps based on what we know. So I'm gonna stop sharing this presentation, and I'm gonna share my browser window, and we'll get to play together with this tool. So prepare your questions about the things that you are specifically interested in, where heat pump makes sense and where it doesn't make sense, because we can test it now. Using this tool, we can evaluate if it does make sense in that situation or not. So I'm gonna stop sharing this presentation. And I'm gonna open my browser. And go to heatpump.cf, and I'm gonna share my screen with you. Excuse me. So here it goes. So heatpump.cf, so the Alaska mini split heat pump calculator. And so let's learn together how to use it. So if you say you are dealing with a building on the market that maybe does have a failing heating system, and the new owner needs to decide what are they going to do about it. Are they gonna just replace it with a new all-fire heating system, or are they gonna put in a heat pump? Maybe the system that's there, maybe it's not failing, maybe it's just old and inefficient, maybe it's gonna be okay as a backup heat source. But if the majority of the heat can be supplied from the heat pump, that could represent significant savings. So if say you are dealing with a building on the market like that, this tool would help you evaluate whether the heat pump makes sense for that building. So Griffin, I see your comment there. Let me just read that. Heat pumps overtook sales of gas furnaces in the US in 2022 and are very common in places like Sweden and Norway. Are there any data from other places showing heat pumps' marginal impact on home values, days on market? In other words, what do we know about how they influence real estate transactions? That's a great question, Griffin. Thank you. Yeah, and like I pointed out at the beginning of this class, so my background is not in real estate. My background is in heat pumps as far as this class goes. So how the heat pumps are going to be affecting the value of the home, that's I'm going to ask you guys, so those of you here with the expertise in real estate. So I would hope that's going to increase the value of the home, because if there's a system that's gonna be saving the new owner energy and money, that should be valued more. And I know there are tools for appraisers to evaluate how some of the energy efficiency features are increasing the value of the home. But in the real world, what that really means, again, that's outside the field of my expertise. So is there anyone here out of you guys, realtors, who would like to comment on that? So if you see a home with a heat pump in it, how do you think that's affecting the value of that home? So I think the answer is that currently it's kind of a new field. We don't quite know, but I think my take on it is to be able to and that's why we have classes like this, is to be able to educate people about the heat pumps and what are their benefits, what are their problems, and then if the potential buyers do see the heat pumps installed in situations where the benefits are outweighing the problems, hopefully that's the case, right? So hopefully we are doing a good job educating people about where to install them, so they are really installed in the situations where they make sense. So hopefully by thanks to classes like these, when people are where the literacy about heat pumps is greater and people understand the value, then they should be valuing the home more and being willing to pay more for that. I think Richard, as you turn on your mic, yeah, if you have things to comment on, please go ahead.
Hey Tom, there's also a great question in the chat about kind of to summarize it, what do we know about how heat pumps influence real estate transactions? And this question is from one of our participants here.
Yeah, thank you, Laura.
Yeah.
Yeah, so I tried to address that. So again, I think it's a new territory, but again, through education like this, hopefully people start to appreciate the value of the heat pumps, and that's going to be reflected in the values of those buildings. And I'm inviting anybody here, those of you with expertise in real estate, to provide more insight on that. Okay, so any other questions or comments from anybody before we go to the heat pump calculator? Okay, I don't see any, so I'm assuming you are ready for the heat pump calculator. So let's have a theoretical example here, and again, I want this to be as useful as possible for you. So I'm going to be asking you for some of these inputs here. So one thing that we obviously have to enter is the location. So at the end, we are using this tool to find out, does a heat pump make sense in a given situation or not? So what location would you guys want to focus on? What town in Alaska? And I do realize we have quite a bit of people here from Fairbanks, and I do see you voicing Fairbanks. So yes, so let's do Fairbanks. So I'm gonna go to Fairbanks here. Then select utility, right? We can do a manual entry, or we can simply just choose what's already loaded for Golden Valley Electric Association, the local utility. So I'm just gonna choose that, and so it has peripheral data for that. It's not completely up to date, but it's still pretty reasonable. And you can there are advanced inputs that you can change. For the sake of time, I'm gonna be mostly using the default values here. I just want you to be available that this tool provides quite a bit of space for adjustments if you want to make those adjustments. So building info, I'm gonna go with the residential building floor area. How big a building would you guys like to evaluate in this? How many square feet? You choose. 1,500 square feet. Sounds good. Okay, I'm gonna go kind of mostly here with the defaults, but if you have a particular interest to go with a different option than the default, let me know. So I'm gonna assume no garage. I'm gonna assume 2x6 wall construction. Select existing space heating, fuel type, and in Fairbanks it would likely be #1 heating oil. So I'm gonna go with that one. Let's say we are only using it for space heating, nothing else. Fuel price about $4.50 per gallon. I don't think it's too far from what it currently is. I'm just gonna keep that. And of course, it fluctuates. So you are not necessarily putting in what it is right now. You are putting in your best estimate what it is going to be throughout the life of the heat pump. Which you make the best estimate based on the current trends and the recent history. So I think this is pretty reasonable. So let's assume it's an 80% efficient heating system. Let's assume it's a hydronic system, so it's a boiler and that has hydronic distribution. Now, if it's an actual building and you know what the fuel consumption is for that building, if you enter it here, it will greatly increase the accuracy of this tool. If you don't know it, that's okay. The tool will calculate it based on the data that you already provided here, like the square footage and type of construction and such. Then the electricity use here, we can keep that as is. And let's see, Griffin says, here's a 2020 study of 500,000 American homes, and that estimates an average 7% bump in value for homes with heat pumps. That's really useful. Thank you so much, Griffin, for sharing that. So I'm just gonna make sure that everybody sees the link from Griffin in the chat with a report showing how a heat pump is increasing the value of a home. Thank you, Griffin. Okay, so here, heating temperature set point, I'm gonna keep it at 70 degrees Fahrenheit. So we're assuming that we are setting your thermostat. Now the heat pump, it can be, if we are talking about these ductless units, those can be single zone or multi-zone, where, you know, for one outdoor unit, you can actually more of those indoor units. I'm gonna go here just with the single zone. You can select a specific model here if you want, or you can just go with a generic model. I'm gonna go with a generic model here for the sake of time. The install cost, you know, it is currently somewhere around $5,000 for a single zone, you know, normal residential size unit like that. Of course, this is gonna vary by community, vary by the specific situation, but, you know, just to if you just want to have a very general number, I would use about $5,000 for a single zone unit like this in an urban location, you know, like Fairbanks. So here, assuming no rebates for now, even though there are likely going to be significant rebates available soon. Again, the state is in the phase of processing the funding coming from the bipartisan infrastructure law and the Inflation Reduction Act. So we are hoping to have significant rebates for heat pumps, and some communities do have some incentives available already. And I'm gonna assume no financing for now. Now let's assume the heat pump is turned off below 5 degrees Fahrenheit, because as we learned, you know, when it's very cold outside, then the fuel that goes into producing the electricity for the heat pump is likely a greater amount than if you are just simply heating with oil on site. And similarly with the cost, you know, when it's very cold outside and you try to heat your home with the heat pump, likely what you are going to pay for the electricity is a greater amount than if you were just heating with oil at that point. So I'm going to leave it at 5 degrees here, but the beauty of this tool is you can play with this point and see what would make sense for your given situation. This also here allows you to set that, you know, you can maybe just choose to use in a simpler way. You turn it off for the winter. So you would choose which months you are turning it off for. Then is the building heated now currently by one space heater, you know, like a Toyo or a wood stove, which means then we would just be, you know, replacing the heat from that unit with the heat pump. So, you know, the whole heating for the building. Here the default is no. It means we are not going to be able to serve the whole building with the heat pump if it's a single zone unit. We are going to be serving a percentage of the building. So the percentage here is adjustable. I'm going to go with the default value of 46%. And with that, we're also setting what's the acceptable temperature in the bedrooms, because if you install a heat pump in the main area of the building, it's still gonna be, you know, if the thermostat for the bedrooms is set to a lower point, it's still gonna be providing some heat. It's gonna be flowing from that main area they are heating with the heat pump to those bedrooms. And excuse me, depending on how much colder you allow them to be, the more heat is going to be flowing in them. And it's also going to depend on whether you keep the doors open or closed. So that's why you're entering it here also. And 0% sales tax in Fairbanks. So we have filled out what we needed to fill out. And I'm going to press on calculate results now, unless any of you has any specific input on what we just put here and want me to change something. Okay, seeing none, I'm gonna hit calculate results. Okay, calculate results, and rate of return 9.2%. So this is good. So this shows that heat pumps are now starting to make economic sense in Fairbanks. It didn't used to be that way. So, you know, I used to say that heat pumps don't make much economic sense in Fairbanks until the war in Ukraine started, when the oil prices went up And since then, heat pumps actually do make a good sense in Fairbanks in a typical situation, or in a general situation like this we are showing here. I'm not saying they make sense everywhere. That's why you have this tool to evaluate where they do make sense, but often they do. So that's the main thing we can see here. So does it make sense? Same thing from the net present value. So these being positive numbers. It shows you how much oil you are going to be saving thanks to the heat pump, how much extra electricity you are going to use because you have the heat pump now. Now the average COP in this situation is about 2.5. Like I mentioned in Fairbanks, we want a COP of at least 2, and here we are above that. So that means it makes sense to use the heat pump in that situation. These greenhouse gas emissions. These inputs are based on the average greenhouse gas emissions from the sources of electricity we have in Fairbanks currently. But what's actually happening, and you could adjust it in those advanced inputs, is that when you install a heat pump in Fairbanks currently, things like the coal-fired power plants are maxed out already. So you are not going to be increasing the consumption of coal. The thing that's likely going to pick it up is the combined cycle plant in North Pole, which is pretty efficient. And based on the data we have from that, with a COP above 2, you are going to be saving greenhouse gas emissions also. So it's kind of a nice thing about Fairbanks is that we have the same number regardless of if you are looking at the environmental impacts or the costs. We can use the same number of COP of about 2. So in Fairbanks, it's not always that way, but in Fairbanks, if it makes sense financially, it's actually also making sense from the environmental perspective. And then it's gonna show you. I'm mainly gonna go to this one where how much you are saving in the individual months. So the green portion will be how much you are saving compared to the situation without the heat pump. So in colder months, obviously lower savings because the efficiency of the heat pump is lower than in the warmer months when you still need heating, bigger savings. Then in summer, when you don't need much heat, obviously, there are not much savings. So this is how you could use the tool to evaluate if a heat pump makes sense in a given situation. And then, like I said, you can also use it how to use the heat pump in a given situation. So, for example, we talked about here the point at which you are going to be turning off the heat pump. Here it's at 5 degrees Fahrenheit. So we can now think, well, what happens if we run the heat pump all the way to 0 degrees Fahrenheit, for example? So you could change it here and then press the calculate button again and evaluate that. So now I have 9.2% and $1,457 net present value. If I change this to 0, we are using it all the way down to 0 degrees Fahrenheit, and I can calculate the results again. So with this generic model that we chose here, which the generic one is one of the most efficient ones, it does actually make sense, as you can see, to operate it down to a little bit lower temperatures. So that's the kind of things you can now evaluate thanks to this tool. So a higher rate of return and higher net present value. So I'm gonna pause here. So this was kind of a just a quick demonstration, but are there any specific questions about this tool and how you can use it to evaluate if a heat pump makes sense, especially as it relates to the real estate market? And any other questions too. So not just about this tool. So I'm going to open this to just general questions about heat pumps. Like I said, my background is not in real estate. It's in heat pumps as far as this class goes. So I'm relying on your questions to lead us to the information about heat pumps that is the most important with respect to the real estate market. So yeah, don't hesitate to ask those questions. And Laura just launched the exit poll too. So yeah, please take a moment to fill that out at the same time. Thank you. Okay, any questions or comments about heat pumps?
Tom, if anybody has any follow-up questions as they're thinking about this information, are you available for calls or emails?
Yeah, they can email me. My email address is on the very first slide. I believe this is recorded, so so if you didn't write it down, it's tmarsik@alaska.edu, but you will see it in that recording too.
Great. Well, thanks so much, everyone. Thanks, Tom, for a great presentation as usual. I know we're seeing a lot more customers asking for heat pumps and wondering about rebate programs and if it will really work in Fairbanks or in Alaska. And we've seen some successes for sure, and that research just continues to get better. So we hope this was a helpful class for you. If you were taking this as part of a CEU, feel free to link into the website there. The $20 will help the processing fee with the state. And if you are just here for your own information, thanks for joining us, and please share our upcoming classes. You can find those at cchrc.org.